So, good evening, everyone. I hope none other will be joining today. So, hope I am audible to you. Am I audible? Okay. So, let me present my screen. So, is the PPT visible? Okay. Then we can start. So, hello everyone. Welcome to the week 13 of live problem solving on GATE Metallurgical Engineering. I am Santara Krishnan, PMRF scholar from the Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Madras. And we will be seeing previous year GATE questions as we have been seeing for the past 12 weeks. So, let us move on to the questions without delay. So the first question for today is the stress required for Orowan dislocation bypass is 200 MPa in an alloy where the interprecipitate spacing is 500 nanometers. So in the same alloy, if the interprecipitate spacing is reduced to 200 nanometers, the stress required in MPa is dash. So this is the first question that we'll be solving today. So does anybody know the equation for the stress required in Orowan dislocation? So you can take 2 minutes to think about whether you know any equation that gives us the stress that is required for neuroven dislocation bypass. So in case you don't have the equation with you, I'll be giving you the equation and then again you can take some time to try and solve it. If neither of this works, then I'll be explaining the whole answer. GB by L. Yeah. So, guys, if possible, please try to unmute and speak so that it's like I don't have to come out of my chat window and see again. So, if possible, try to unmute and speak. So, if the equation you have given is correct, that is the stress required for neuron dislocation bypass is tau is equal to GB by L. So, in that case, G is the shear modulus, B is the Burgess vector, and I is the interprecipitate spacing. So if the equation is correct, now you have to substitute and find out the interprecipitate spacing when L is 200. So can you please solve and let me know the answer? Yeah. So is the other person people also getting the same answer as 500? 500 is the correct answer. So what about the other people? Are you getting the same answer? Okay, fine, fine. Okay. So the case is that keeping G and B constant, O weight is as tau 1 by tau 2 is equal to L1 by L2. So in our case, they have given us tau 1, we have to find tau 2. It is 200 MPa and L1 and L2 are 500 and 200 nanometers respectively. Therefore, on substituting, we have 200 divided by tau 2 will give us 500 by 200. So hence, the tau 2 is equal to 500 MPa. Therefore, to that particular question, we can say that the stress required to move the rho1 dislocation is 500 MPa. So I hope this is clear to you. Now we can move on to the next question. So It's a very simple, direct question. It was asked in 2012 for 2 marks actually. So this is a stress cycle. So given the stress cycle, the stress ratio and amplitude ratio is. So for the stress cycle given in the image, the stress ratio and amplitude ratio is dash. That is what you have to find out. So once you get the stress ratio, you can find the amplitude ratio. So can somebody give me the equation for stress ratio and amplitude ratio? Stress, yeah. And what about amplitude ratio? No, once you get the stress ratio, how to find the amplitude ratio from this given information? Here they have given us only stress value. So if you have the stress value, you can get the stress ratio. That equation is correct. Once you have the stress ratio, from the stress ratio, you can find the amplitude ratio. So what will be the equation for that? So the first part is correct. That is, stress ratio is sigma min by sigma max. Therefore, it will become minus 100 by 50. Therefore, it is minus 2. It's correct, right? You're getting the same answer, right? Yeah. So in that case, once you get the stress ratio, how do you find the amplitude ratio? Yeah, that's correct. Yeah. So is the other person familiar with the equation? Yeah. So once you know the stress ratio, the amplitude ratio is given by 1 minus r by 1 plus r. So in that case, what will be the answer? I hope you have started practicing solving these questions on gate calculators itself. Yeah. So the answer will be minus 3. So is the question clear to all of you? Like whoever is there? Yeah. So what about the other person? Is it clear? Okay. So the next question is, in a brittle material, the maximum internal crack length is 8 microns. If the Young's modulus is 400 GPa and surface energy is 3.14 joule per meter square, the estimated theoretical fracture strength in MPa is given as four options are there. So it's a brittle material, the maximum internal crack length is given, Young's modulus is also given, and surface energy is given. So, what is the theoretical fracture strength? So, first, what is the equation or the theory that we use in solving this kind of questions? There's a particular equation. Yeah. So, how do you identify that it's Griffith theory? Yeah. So whenever there is a word brittle material or based on the input that is given to you, that is maximum internal crack length, Young's modulus, and surface energy. If you know the Griffith equation, you can identify from the given, or you can say based on the fact that it is a brittle specimen. From these two factors, you can say that you can solve this question using the Griffith criterion. So now that you have told it's the Griffith criterion, can you please tell me the equation? Yeah, where A is the okay. Okay. Yeah, that is correct. So, what is the Griffith criterion actually? So, a crack in a brittle material will propagate when the reduction in potential energy that occurs due to the crack growth is greater than or equal to increase in surface energy due to creation of surfaces. Just for understanding, the thing is that whenever there is a crack in the material and when it grows, it will lead to the creation of two new surfaces. And the creation of these two new surfaces requires energy. So, how do we get this energy? This energy will be taken from that energy that is released, that is the potential energy that is released as the crack grows. So whenever these two energies are at least equal or if they are greater, the crack will propagate. So that is the Griffith criterion. So this is the usual image that we use for explaining the Griffith criterion. So the theoretical fracture strength, as you said, is given by Fs is equal to 2e gamma s by pi c, where E is the Young's modulus, gamma s is the surface energy, and c is the crack length. So one thing that you have to take care while solving Griffith criterion question is that if it is an edge crack, c will be the total length of the crack, and if it is such a center crack, whatever that is given to you will be 2 times c. So while substituting, you will have to take half of this. So is that clear for both of you? Yeah, what about the other person? Since only two are there, it's better. Yeah, okay. It's better that we have an interactive kind of session. If there are more students, means okay. So, in that case, now that you have all the required values, can you please try solving with the given values? Yeah. What about the other person? Okay. So, given that 2C is 8 microns, that is 8 mu m, we have to convert. Somebody joined, I think. Okay. So, given to us 2c is equal to 8 microns, therefore c will be half of 8 microns. So since it is given that it is an internal crack, whatever we are substituting in the equation will be half of it. We have to convert all values into SI units, therefore c is equal to 4 into 10 power minus 6. Also he is given as 400 GPa, that is 400 into 10 power 9 pascals. Then we have gamma s, that is given as 3.14 joule per meter square. And since all these values are given, theoretical fracture strength is equal to 2e gamma s by pi c. Upon substituting, you will get the value as you mentioned as 447 MPa. So is that clear to both of you? Okay. So in that case, we can move on to the fourth question. A brittle material again is mechanically tested in a medium P, which has surface energy as gamma S is equal to zero point 0.9 joule per meter square. This material has a fracture strength of 300 MPa for a given flaw size. The same solid containing some same flaw is tested again in medium Q, where the gamma SS is given as zero point 0.1 joule per meter square. The fracture strength in medium Q based on Griffith theory is. So, since you already know the equation from the previous question, please attempt and tell me the answers. It is already mentioned here that we have to use Griffith theory. Okay, and what about the other person? Am I getting the same answer? Hello, am I audible? Okay, okay. And the answer is same, right? Okay. So basically, according to Griffith criterion, theoretical fracture strength FCFS is given as 2E gamma S by pi C the whole power 1 by 2. So where E is the Young's modulus, C is zero point 0.5 of crack length for internal crack, and gamma S is the surface energy of the material. So keeping E and C constants, we can say that Fs varies with gamma S, that Fs1 by Fs2 is equal to root of gamma S1 by gamma S2. So in that case, when we substitute, we have Fs1 as 300 MPa. Fs2 is the one we have to find out. For medium P, gamma S1 is given as zero point 0.9 joule per meter square, and for medium Q, gamma S2 is given as zero point 0.1 joule per meter square. Upon substituting, we will be getting 300 by Fs2 is equal to 3, and hence Fs2 is equal to 100 megapascals. So I hope both of you got this answer, and in that case we can move on to the next question. So, creep resistance decreases due to a small grain size, fine dispersoid size, low stacking fault energy, and high melting point. So, in case you know the answer, I would like to know like the reason for the answer that you have selected as well. So, creep resistance decreases due to which of the following factors? There are four options, and you have to tell me the reason along with answering why. The reason is okay, yeah, less, yeah. So, does the other person also agree with the same answer? This is actually a revision question. I had already solved this once, I believe. So, in case there is any doubt, I'll just go through the theory once. So, creep, what is creep? We all know it is the tendency of the solid material to deform slowly and permanently under mechanical stresses at elevated temperatures, right? So, the temperature at which material starts usually depends on their melting point. Why do we say that? Because we know for materials like mercury, room temperature is high enough that it is in the liquid state, but for most other materials, room temperature according to it is low temperature. Therefore, we define something known as a homologous temperature, where we divide the actual temperature by the melting point temperature, and whenever this homologous temperature reaches a certain value, materials will start to creep. And usually for most materials, it is found that for in case of metals, creep will occur when the temperature is greater than zero point 0.3 to zero point 0.4 times of the melting point, and for ceramics it is zero point 0.4 to zero point 0.5 times. In that case, we define what is known as an equicohesive temperature. So, can neither of you tell me like what is an equicohesive temperature? You might have studied in theory. Grain boundaries, exactly. So, equicohesive temperature means that temperature below which the at the equicohesive temperature, we can see here that the strength of both the grain boundary and grain interior will be the same. So, below the equicohesive temperature, then what will be stronger? Grain boundaries will be stronger, and above the equicohesive temperature, grain interior will be stronger, and therefore below the equicohesive temperature, transgranule, that is fracture, will happen across the grains, and above the equicohesive temperature, intergranular fracture will take place. So we can say that below equicohesive temperature, finer grains will be strong, and above equicohesive temperature, coarser grains will be strong. And hence, also, instead of solving this question theoretically, there is another equation that we can use to define such questions, where there is an equation for creep resistance. So, does either of you know the equation for creep resistance? This is the theoretical way of explaining how we got that answer. There is another way, that is using a particular equation. So, does either of you know the equation? Yeah, it is a rate equation. Straight, yeah. So basically, the equation. Oh, sorry. We'll come to this slide next. This is the equation that we use. So d epsilon by dt is equal to c sigma power m by d power b e raised to minus q by kt. where epsilon here is the creep resistance or the strain rate, and C is a constant dependent upon the material and mechanism. M and B are exponents again dependent upon the mechanism. Q is the activation energy, and sigma is the applied stress. D is the grain size of the material, and K is the Boltzmann's constant. T is temperature. So if you know the equation from this equation also, we can see here that d epsilon by dt is inversely proportional to d power b, and d epsilon by dt gives us the creep resistance and dB gives us the size of the grains. Therefore, due to this inverse relationship, we can say that as the grain size in the creeping state, as the grain size increases, the material will be more creep resistant. Hence, we can say from the equation that creep resistance decreases for smaller grain size. Is it clear? Yeah. And these are a few points that we can say with regard to the same question. Grain boundaries are not desirable for high temperature structural applications. This is because grain boundaries are regions of high energy. Under normal conditions, we say that smaller fine grains will be useful. Means from the Hall pitch equation, we say that finer grains will be having more strength, right? Yield strength will be more. But that is because even though being higher energy, normal temperature diffusion conditions will be such that grain boundaries can arrest the moment of dislocation and thus increase the strength. But when materials are heated, what happens? Vibrations become more, there will be more amount of thermal diffusion happening, and hence grain boundaries become weaker and they will slide past one another. And that is how the material fails at high temperature. Therefore, fine grains material will be used in the normal temperature condition, and coarse structured materials will be used for high temperature application. Is that clear? Yeah. So 1 minute, I just need to stop presenting. Can you please give me 2 minutes? Yeah. So is my screen visible? So this is one more question we can practice on similar grounds. So a plastically deformed metal crystal at low temperature exhibits a wavy slip line pattern due to which of the following reason? Dislocation pileup, large number of slip systems, low stacking fault energy, and dislocation climb. So it is given that a plastically deformed metal crystal exhibits wavy slip line pattern. So why do we see such wavy slip line pattern? So it can be due to dislocation pileup, large number of slip systems, low stacking fault energy, or dislocation climb. So I think I've discussed a question, similar question in the past. So, or you can give any wild guesses, just in case. A or B. Okay. So the guess is right. It's due to the large number of slip systems. So now we'll go to the reason. So basically, first we need to know what is a wavy slip line pattern and how the entire thing looks. So basically, when slip happens, so this is the crystals and this is a slip plane. We know the slip direction and normal to the slip direction. And during the process of slip, we know that there is something known as Leuder bands, right? There will be large number of bands forming, and these bands are due to the fact that the critical resolved shear stress will be exceeded in those planes excessively, and that is how these kinds of slip lines are formed. So basically the terminology is that this is the spacing and this is the slip band width. So here you can see this is the slip band width, this is the entire spacing width, and these are the lines that will be formed. So atoms in a metal move integral number of atomic distances along the slip plane, resulting a step. So whenever a dislocation is moving inside a material, it is not that the atomic planes slip all at once or they give an entire movement. They actually move integral distances. That is, first they move a small distance to a new plane, and then again the stress value will be exceeded. They'll move to the next. So we can say that it moves in integral number of atomic distances, and each of these step will appear as what is known as a slip line. Therefore, we can say that slip does not occur on one plane but over a region of parallel planes, and together it forms what is known as a slip band. So here itself there is a thing. See, it doesn't happen on one plane, right? So we all know that one plane plus one direction gives us the slip system. So this itself is a hint that it is due to the large number of slip systems in the material. So slip line patterns are line that appear on the. So how do we physically see a slip line pattern? This appears on the polished surface of a crystal or crystalline body that has been stressed beyond the elastic limit, and they represent the intersection of the surface by planes on which shear stress has produced slip or gliding. So this is from the slip system. So basically the thing is that instead of moving all at once, the dislocation will be moving one slip system at a time, and on each of these systems the critical resolved shear stress will be exceeded, and each of them will exhibit macroscopically as a line, and together they form what is known as a slip band. Therefore, from here itself, it is clear that a plastically deformed material at low temperature exhibits wavy slip line pattern due to the large number of slip systems. So, is that clear? Yeah. Okay. And in between, I just wanted to ask, have you got any information from NPTL that till what time you will be having the live sessions or anything like that? Okay. Your exam is scheduled on? Okay. For both of you. Only one date is there for MT, right? Okay. So if you see it till then, you'll be having some, how many classes left? February 11th means three more. Actually, there are three more Thursdays left, but I also haven't got any information from NPTL. Like out of these 3 weeks, how many more weeks we have to continue or not? And are the other sessions happening on the other days as well? Okay, I think Kamesh might be knowing the timetable on what all days actually these NPTL classes are there. I think there are a few other scholars also taking for MT. I'm not sure. Sunday, Monday, and Thursday. Okay, fine. So these sessions are going on right now. Okay. So yeah, once you get any communication, I hope like both of us will be informed at the same time, I'm thinking. So I think we have discussed some 5 to 6 questions today, and I hope you're clear with the concepts. And while trying to solving the problems, please try to use gate calculator always. So it will help you speed up during the examination. So thank you for both for joining. So hoping to see you next week as well. So thank you so much. Yeah. And in case you and in case you have any suggestions or feedback, also please do let me know. Yeah. And do you know the mail ID? Okay. Yeah, yeah, I can share the mail ID with you. So is the screen visible? Yeah, so any additional queries and feedback also you can mail to this mail ID and inform me directly. And in case I handle physical metallurgy and mechanical metallurgy, in these two areas, if you have any particular question that you want me to solve, you can just tell me the year and the question number, and I can solve and present that as well. Or any concept related question or anything. Yeah. So thank you so much for joining. Yeah, thank you.